All right, this is AQA, AS Level Physics, 2022, Paper 1. As per usual, I can't show the paper on screen because otherwise AQA will get my channel deleted like they always did in the past. So, link to the paper and mark scheme are in the description. 1.1, we have this table of various things. Okay, what the sigma, and we have baryon number, charge, and strangeness. And here's what we know already. Of course, it's both of these things going to make both of these things, isn't it? So first baryon number for a pion. A pion is a meson. It's only made up of 2 quarks, not 3 quarks. So therefore, its baryon number has to be 0. It's not a baryon. Strangeness, well, a pion is a meson that doesn't have strangeness, whereas a kaon is one that does have strangeness, so we can just put 0 for that. And I should probably write down here that it's a strong interaction. That's going to be important for the strangeness. Proton is a baryon. It's not an antiproton, so it's just +1 for the baryon. And in order for baryon number to be conserved, that means that the sigma plus must be a baryon and have a baryon number of +1 as well. Charge, well, if we want that to be conserved, then the charge of Y must be +1 as well. And then strangeness is the one that's going to be a little bit tricky. No, actually, because it's just a strong reaction, that's fine. Proton doesn't have any strange quarks in it, so that's going to be 0. And we want strangeness to be conserved. We already have +1 there, so it's going to be -1 for the sigma plus. 1.2, which one of these is UUS? Well, we know that a strange quark has a strangeness of -1. Strange quarks are strange. They're the ones that sort of like buck the trend. Normal particles are +1 for everything apart from strange quarks. Strangeness, -1. Anti-strange, of course, +1. So therefore, it has to be the sigma plus. Which one of these has the greatest charge to mass ratio? So charge divided by mass. So in order for this to be the largest, we need charge to be big and mass to be small. So we know that Y is a meson. It has to be because it's got a baryon number of 0, and it can't be a lepton because, well, there's no other leptons involved, and it's a strong interaction as well, so therefore there can't be leptons involved. And so we have, well, it has a strangeness, doesn't it? So it is going to be a kaon, and it's got a charge of plus, so therefore it's going to be K plus. We're not too concerned about that. So we're going to have to look at the masses, aren't we? And we are going to have to look at the formula sheet, actually, because we're going to need to know the masses. It's not very often that we have to look at the masses of mesons. So we can see that a pi plus has a mass of, or a rest energy, that's just mass turned into energy, of 139.576 megaelectron volts, whereas the K plus is, oh, that's quite a bit bigger. So 493.821, not that we care about the points, but there we go. So therefore, K plus has larger rest energy, therefore larger mass. Therefore, if it has a smaller mass, then therefore it's going to be a smaller ratio. Therefore, pi plus has larger charge to mass ratio. 2.1, we have gas, and it has 2 isotopes. The gas is ionized. Explain how the beam of electron causes a particle to have a charge of +1. So we have free electrons, or a free electron, I should say, in the beam, collides with an electron on a gas atom, giving it enough energy to leave the atom, and it's been ionized. As electron charge is -1e, ion left with +1e. Easy peasy. 2.2, we have a graph of number of nucleons. Oh, I vaguely remember this one now. I think this caught a lot of people out. What's nice is that they've given us nice numbers, 25, 25, and 50, so that's pretty good. So what are we being asked? So bromine has a proton number of 35. The 2 isotopes in the sample have different nucleon numbers. Right, so what you've got to remember is that bromine gas is Br2, and so therefore they go around in pairs. If they ended up being 158, then what does that mean that the 2 isotopes have to be? Well, they have to be 79 and 79. If they're 162, then that means that they have to be 81 and 81. If they're 160, well, they have to be 79 and 81. Those are the only options because we know that there are only 2 isotopes, so that has to be the isotopes. So we're being asked, calculate the number of neutrons for the isotope that has a greater nucleon number. So nucleons, that's going to be 81. Protons, that's going to be 35. We're told that. So therefore, neutrons, so this particular isotope is going to be that. And so neutrons is equal to 81 minus 35. And that gives us 46. Not a super easy question, because a lot of inference that you need to make there. 2.3, deduce the percentage of each isotope in the gas. Okay, so like I set up here, it can be 79, 79, 81, 81. Yes, 79 and 81, but there's another option, as it were, and that is 81 and 79, because they can just be the other way around. And that is actually quite important. The point is that this makes up 25%. This makes up 25%. And both of these together make up 50%. And so that means that individually they're 25%. And so actually that means that there's just 50% each. So they all have an equal probability of being in the gas. Of course, you would have to put that down in words a little bit more than I have here. 3.1, oh, what is going on here? We have an ice sheet and surface of ocean. I think this is interference. Frequency is that. And we're told that the duration of each pulse, so time for each pulse, is 6 times 10 to the minus 3 seconds, 6 milliseconds. Calculate the number of cycles in each pulse. Okay, so that just means basically how many time periods in each pulse. Fine. So this, of course, is also the same thing as seconds to the minus 1. And so therefore, we're just looking for a number. And so we want no units. So units are your friends here. And so we could say here, we could say cycles per second. So if we do 3.8 times 10 to the 14 cycles per second, and then we multiply by 6 times 10 to the minus 3 seconds, then the seconds cancel out and we're just left with cycles. Oh, I read that as milliseconds. It's because the screen is far away from me. Nanoseconds, that's minus 9. What a silly Billy. There we go, that's a bit better. And that gives us 2.3 times 10 to the 6 cycles. Okay, I think we're going to have to do some path differencey stuff here now, guaranteed. There's A and there's B. So 3.2, they return, the travel time is the time between the emission of a pulse and its return to the satellite. So it's going like that. And also it's going like that. So there's our path difference there. That's double the height, isn't it? Okay, the difference between the times is that many microseconds. That's fine. There we go. We can figure this out. So we're not using wavelength here. So it's not c equals f lambda. We might as well just use just distance equals speed over time. That's fine. Or in this case, it's going to be c is equal to 2 lots of the height, because that's the path difference, divided by the difference in times for both of these. And so therefore just swapping, and so therefore we want to rearrange for h. So therefore h is equal to c delta t divided by 2. And so that's 3 times 10 to the 8 times by, what's that, 10.7 times 10 to the minus 6. Why not tidy up some powers of 10? And then divide that by 2. So I think that's essentially 300 divided by 2. So I'm just going to say that's 150 times 10.7. Oh, I could nearly do that in my head, but I don't think I will be able to. That seems like a very high shelf, doesn't it? They give us 1,605 meters. Also 3 sig figs, we can just say it's that. So yes, quite often with interference or path difference questions, we're just using speed equals distance over time, not v equals f lambda. 3.3, we have a bit of refraction going on now. The normal there, and there's our ray coming in straight down, and then it's going like that. Not a very big difference, but I'm exaggerating it a little bit so you can see it. There's our 38. That's not going to be our angle of incidence, if you can see, because that's not between. Oh, so yeah, there we go. All right. So we don't care about this. We are going to have to take it away. And so therefore, this is going to be equal to 90 take away 38. So 90 take away 38. And so that gives us 52 degrees. Is it me, or have they been really cheeky with the lines? They've made it look like it's not much of a difference to make it look like the angle of incidence and angle of refraction are very similar in 38 and 37 degrees. That's really, really mean, if you ask me. Okay, we haven't even looked at the question yet. Calculate the refractive index of the ice. Oh, well, there we go. That's easy. Start with Snell's law. I always like starting with this. So what does this end up being? This ends up being 1 times sine of 52 equals n2. That's what we're looking for. So I'm just going to call that n times sine of 37. So rearranging this, 1 disappears, of course. N is equal to sine 52 over sine 37. And that gives us 1.3, let's say. So yes, they're trying to catch you out with the diagram and the angles. So just be wary that you could be given angles that are different from the actual angle of incidence and refraction. If we did do sine 38 divided by sine 37, if we got it wrong, what would we end up with? I'm just curious. Yeah, we get a very low number, of course, because they're very similar. So 1.02. If you got that, then alarm bells should be going off in your head. You should be saying, hang on a minute, that's a very low refractive index. That's very similar to air. That can't be right. So sanity check your answers, ladies and gents. Very good thing to do. 3.4, calculate the wavelength when it is inside the ice sheet. Okay, we're going to need a different version of refractive index here, and that is speed in air divided by speed in the medium, isn't it? We could find out the speed in the medium, but do you know what? Let's actually just say C equals F lambda. So what we can do is say that, well, we know this already, don't we? And we know this. And so what I can say is that the speed of the light, or the infrared radiation, of course, in this case, inside the block is going to be equal to frequency times the wavelength in the block. So I can just replace CS on the bottom with that. Of course, frequency stays the same. We know that for a refraction, don't we? Speed changes, wavelength changes, but frequency does not. We're looking for this. I'm just going to swap around n and lambda s. So therefore, lambda, do you know what? I'm just going to call it lambda. Lambda is equal to c divided by fn. So that is 3 times 10 to the 8 divided by, what's our frequency? Oh, I'm going to go miles back. I mean, for you, it's just on the other page. 3.8 times 10 to the 14 times by our refractive index of 1.3. Yes, I'm going to tidy up powers of 10. This ends up being minus 6. And I end up with 6.1 times 10 to the minus 7 meters. Of course, you could have just found the speed and then just done 2 calculations. That's fine. So, nice 6 marker. We're just being asked to explain the photoelectric effect. Nice. So, photons incident on the plate are absorbed by electrons in the plate. Energy of each, and this is something that people often don't write down. You get a mark literally just for writing down energy of each photon, E equals HF. Always write that down. You'll get a mark for just writing that down. Electrons are only liberated when frequency is above threshold frequency, and we can call that F0. Or in other words, that means energy of each, this is probably another mark in itself, is greater than the work function phi. Therefore, as electrons have charge, plate loses charge. Of course, it's negatively charged, so it has lots of electrons, more electrons than it would do normally. Okay, we've done the second point. The rate of loss of charge increases with intensity. Okay, so intensity affects rate of photons incident on metal. This does not, and this is the important bit, this does not affect the energy given to each electron due to one-to-one interactions, but does increase, or but does affect rather, rate of electrons liberated and therefore rate of charge lost. Easy. Again, we could say if the frequency is above the threshold frequency. 4.2, charged particles. Okay, we have a maximum kinetic energy of 1.1 electron volts. We won't change that for now, just in case. Yeah, because we are being asked for the answer in electron volts, so we're going to leave it as that. So it's better to change the frequency. We're told the frequency is 1.2 times 10 to the 15 hertz. You could change it into joules and then go to the whole thing, but you're just going to have to convert it back afterwards anyway, so there's not much point. We'd better to do one calculation rather than two. So let's get our equation. EK max, that is, equals HF minus phi. We're looking for this, so therefore phi is equal to, just going to swap EK max and the phi, so HF minus EK. I'm going to drop the max. And so, well, we need, all of these are in electron volts. This is an energy, this is an energy, this is an energy. We're looking for this in electron volts. This is already in electron volts, so we're going to need to convert this into electron volts. So therefore, I'm going to say 6.63 times 10 to the minus 34 times by 1.2 times 10 to the 15, and then we need to turn this into electron volts. So our conversion factor is 1.6 times 10 to the minus 19, and we're going to be multiplying or dividing. Well, we know we want a bigger number because electron volts are small, so therefore we're going to be dividing. Sort of gave the game away there. And then take away 1.1. Let's tidy up some powers of 10. We know they're all going to cancel, so we're going to end up with just a nice number that's between 1 and 10 probably for the electron volts here. So minus 19, add that onto the top. Yeah, sure enough, that just ends up being 34. So both of those cancel. So it's just going to be 6.63 times by 1.2 divided by 1.6. And I end up with 4. Ooh, and now I should probably call that 5. To 2 sig figs, that's 5 anyway. Take away 1.1, that gives us 3.9 electron volts. Like I said, you could have converted the kinetic energy into joules, but then your work function would be in joules. Then you need to turn that back into electron volts. It's doing twice the work. 5.1, we have electron diffraction going on. Fine. What are we being asked? State and explain at which P, Q, R are the electrons are demonstrating wave-like behavior. That's a bit of a funny one, I guess. I mean, obviously it's R, isn't it? Explain why interference is occurring to produce maxima and minima. That's why we get the bright and dark fringes, much like with light, for example, with the Young's double slit. However, you would be forgiven for thinking that Q, we could say as well, because diffraction occurs here. The problem with that is that technically, even if they just acted like particles, they would still be deflected, but deflection would still occur for particles. I'm sorry, the mark scheme actually says Q. I am at a loss for words. I really have no idea what they're smoking over at AQA. So the answer, if they really want to go down that route, the answer has to be Q and R. You cannot get maxima and minima unless these electrons are acting like waves. You literally have electrons arriving at the dark fringes as well, but they're producing a dark fringe because they're cancelling each other out, because they're arriving at antiphase, because they're acting like waves. My word. Let's see what the mark scheme says. Treat interference at R as neutral, but it's not. As in, like, you don't get a mark for that. You don't get marked down, though. This is silly. They're wrong insofar that it has to be R as well. That's a stupid question. The apparatus is adjusted so the electrons are incident with greater speed. Okay, fine. So we're talking about lambda is equal to h over mv. So if v increases, then that means lambda decreases. And as a rule of thumb, if lambda goes down, theta goes down. If we have a look at our n lambda equals d sine theta, of course this is for a diffraction grating, but it's the same sort of deal. We can see that lambda and sine theta are proportional. We could say, of course, lambda is inversely proportional to speed. That's it. So smaller angle. They actually go down the route of saying that wavelength is closer to gap between graphite layers and between the graphite layers, and you should know that the closer a wavelength is to the gap or the thing that is going round, then the more diffraction you get. That's why I say that this is very much a rule of thumb, because it's very unusual for us to have a wavelength that is smaller than the gap. That was a dumb question. My days. 6.1, yeah, actually some proper stuff now. Right, we have a dude on a window washing thingy. Oh, that's fun. Okay, so there's our situation. We are going to have to put on here the weight of the bar as well, guaranteed. I haven't even looked at the question yet, but I know that's going to be there. It's going to act from the center of the bar, isn't it? I'm going to call that W. Okay, what are we being asked? The platform weighs 1800. There we go. So let's see if we can just put 1800 newtons there. Okay. Each cable has an unstretched. Oh no, it's one of these again. We're going to have to do materials as well. So the length is 3 meters. The distance between P and Q is 3.6. We know that. So the whole thing is always going to be horizontal. Right. Okay, fine. So we don't have to do with any angles. The worker moves to a position where the tension in the left-hand cable is 1150 newtons. Right. So we have 1,150 newtons being pulled up there. So therefore, we're going to make B our pivot. That's all we have to do. Easy peasy. So we're ultimately going to find that and then take that away from 3.6. So let's find this distance, shall we? We have the 1,800 times by 1.8. So that's half of the distance, of course. to the center of mass. Of course, that's an anti-clockwise moment. Let's add the other anti-clockwise moment. That is 750 times by, I'm going to call this distance just x, that's fine. And then that is equal to 1150 times by 3.6. Okay, so rearranging this, would you allow me to say that this is 900 times 3.6, because that's going to be useful in a second. So I'm going to rearrange to find x. So x is equal to 1150 times by 3.6 minus 900 times 3.6. You see why I did that? And then just divide that by 750. And so that's going to be, what's that? 250 times 3.6 divided by 750. And so I think that's going to be a third. So basically 3.6 divided by 3. And so that gives us 1.2. Wow, I didn't even need a calculator. How smart am I? So that's what x is there. So if that's 1.2 meters to there, ooh, he's the other side. So he's actually here now, methinks. That's okay. And so therefore, d is equal to 3.6, take away 1.2, so 2.4 meters. Oh, I'll quite chill for that. Okay, we now have the materials bit of the questions. Okay, so we have extension against distance. Oh, this looks complicated. I'm going to put x. Am I? Yeah, it's a different x from earlier, but yeah, that's fine, I think. Okay, there's our line going down like that. So what are we being asked? Determine d. Okay, the work it moves to position with a strain in P is 6 times 10 to the minus 5. Now, strain is equal to change in length divided by original. So I'll tell you what, let's call this delta L here. So we're looking for delta L. So therefore delta L is equal to strain times the original length. And so that's 6 times 10 to the minus 5 times by our original length. We had that earlier and that was 3 meters. So therefore this is just going to be 18 times 10 to the minus 5, or 1.8 times 10 to the minus 4, or in other words, 0.18 millimeters. So just reading off the graph, that gives us, I think it's just 1.8 meters. There we go. 6.3, we have a Young modulus of this, and we're going to be asked to find stress, no doubt. So when this guy is at x, and so Young modulus is equal to stress over strain, we're looking for that. So therefore, stress is going to be equal to strain times the Young modulus. This is a nice question. This is probably one of the nicest questions ever. And so it's just going to be 6 times 10 to the minus 5 times the Young modulus. This just ends up being times 10 to the 6. So I think we're going to end up with 1.2 times 10 to the something. Let's just do it real quick. So 6 times 1.9. Oh no, not quite. Whoops. Of course, it's going to be less than 1.2. The doi. So 1.14 times 10 to the 7. And again, that's in newtons per meter squared. 6.4, the cables are replaced. R is halved and the Young modulus is doubled. This is more like a multiple choice question, actually. And so if R has doubled, because area is what we are concerned with, and area is equal to pi d squared, or sorry, pi r squared, yeah, or pi d squared, if it doesn't matter. That means that area, that quarters, because it's r squared. Okay, so we know what's happening to r, we know what's happening to e. Unstretched length is the same. Okay, we're just being asked to draw the new graph for the new wires. That should be fairly easy, methinks. So there's the one for our original, I think. And okay, so we're walking from A to B, but it's more than just A to B. It's a nice song. Weird though. My guy called Matt Hyers. Anyway, what are we doing? We've got extension here, so I'm just going to put delta L, and we have D there. Okay, let's have a think about this. So extension is equal to, yeah, stress over strain, and so that's equal to FL over A delta L. We're concerned with what's happening to delta L, so therefore, rearranging this, do you know what? Actually, I'm going to just put first, what's staying constant? Unstretched length is the same, so therefore we can say E is inversely proportional to A times delta L. We're concerned with what's happening to delta L, so therefore delta L is inversely proportional to the area times the Young modulus. So what did we say? We say this is quartering, but this is multiplying by 2, so therefore this whole thing on the bottom is dividing by 2, but if that's dividing by 2, that means the whole thing is multiplying by 2, so therefore the extension is going to be bigger as well. So that means that we're here at 0.23. So that means that every value basically is going to double. So therefore, our new line is going to start here. Where is it over here for P? 0.13. And so therefore, it's going to go to 0.26. So therefore, our new line is going to look something like, I haven't done a very good job on the scale, but you get the idea. It's going to look something like this. Cool. Yeah, like I said, that's more of a multiple choice question. That is just that we're adding in the graph. 7.1, cyclist up a hill. We have an angle. The mass is 65 kilograms. And write an expression for the components of the total weight parallel to the slope. I have a whole video on this, masses on slopes. But all you need to know is that... oh boy. All you need to know is that the components of the weight pulling down is mg sine theta. Fine, you want me to prove it to you? Let's draw a triangle like this, and then we draw the component going perpendicular to the slope. There we go. So basically there's our resultant, that's our weight, that's mg, and then there's our component going down the ramp, and there's our component going perpendicular to the ramp. And there's a right angle triangle. This has to be this way around. And so therefore theta is going to be there as well. People say, well, how is that the case? Well, that's because this is 90 degrees. So therefore this is going to be 90 take away theta. So I'm just going to call that phi. And so therefore this angle here has to be 90 take away phi, which of course is going to be equal to theta. So there we go. But that's something just worth remembering. Component of a force down the slope, always mg sine theta. 7.2. Useful power is, I'm just going to say power out. I'm going to need that? No, I'm not. It's just saying useful power out. That's fine. 310 watts. The cyclist has a steady speed of this. Calculate theta. Fine. Nice and easy. We have power. We have velocity. Therefore, we know we're talking about work done, or in other words, a power version of that. So work done is E, because it isn't energy. I just like calling it E. I don't like calling it W, because that's for weight. E equals FD, but if we divide both sides by time, then we end up, you have this equation, so you don't need to worry about it, but we have power is equal to FV. There we go, and we know that this is equal to mg sine theta, because if he's going at a steady speed, I assume it's a he anyway, therefore we must have a force being produced to pushing him up the slope of mg sine theta as well. So therefore we have this. We're looking for theta, so therefore I'm going to say sine theta is equal to P over mg v. And so therefore I'm just going to say theta is equal to the inverse sine of, so P power, what was that, 310 divided by 65 kilograms times by 9.81 times by 1.63. Let's pop that all in, see what we end up with. I end up with 17.4 degrees. I can probably just leave it at 17. Sounds like a normalish angle. Sanity checking it. Figure 9, zigzag, taken by the cyclist. She maintains, there's my toxic masculinity. She maintains a steady speed of 1.63. Discuss how useful power out when taken apart compares with useful power out. Well, of course, it's not going to be as useful power out, is it? So cyclist is using more of her input power. Cyclist is using less of her input power to cycle uphill. More some being used to go sideways. So therefore we can say that P out is less. Therefore, what did we say that was equal to? We said it was equal to mg sine theta v is less. What is staying the same? This is all staying the same, constant. And so therefore, v in direction uphill decreases. That'll do. Not a very nice question, that one. Again, just this whole vague, what would happen? Compare this without doing any calculations. Okay, we have a graph of this, and we have v there, and we have time there. What are we being asked? Determine the acceleration. Oh, okay. Well, acceleration is equal to, what am I writing acceleration? A will do. A is equal to delta V over T, of course. And so in our case, that's going to be equal to the gradient. And so it looks like we're going to have to draw a tangent. So if we draw that at 10 seconds, so all I want to do is draw a tangent. You can always turn a piece of paper if you want to. It's a useful thing to do. So you're drawing the tangent horizontally. And you should end up with a gradient for that tangent of about 0.21 meters per second squared. 7.5. Oh, what's with the righty questions? Ooh. Energy transfers occur as the cyclist travels. Outline how these energy transfers explain the shape of the graph. Okay, so acceleration is decreasing. Okay, so acceleration is obviously decreasing as we get faster. Acceleration decreasing with increasing velocity, despite mg sine theta constant. So why is this? Well, it's because of terminal velocity, isn't it? And drag forces. Therefore, resultant force downslope decreasing due to drag forces. Well, that could be friction, air resistance, acting upslope or opposite to velocity. These increase with speed, reducing acceleration. I'm repeating myself a little bit, but it's a 3-mark question for some reason. Oh, we need to talk about energy, I guess, don't we? Okay, fine. So kinetic energy. Okay. So potential energy, I guess we should say GPE, converted to KE, but also transferred to air due to air resistance, and e.g. heat in bearings, for example. There we go, that'll do. Question 8, electricity to finish off. So we have this circuit. Let's see if I can draw it nice and neatly. I could be patient and draw proper lines, but nobody got time for that. Okay, ammeter there. Oh, I've done a terrible job here. Okay, P, X, Y, and we have a voltmeter across the bulb. Very neat science shorts. Calculate the resistance of the lamp when the voltmeter reading is 0.75. Okay, so this is 0.75 volts. We're told that this is 25. I'm just going to call this R. So R max. That's 25 ohms. And so, okay, so we need to find out the current, don't we? Of course, we want resistance, so therefore we have to find out current if we have voltage. Okay, so 0.75 volts there. So that means across here, I don't think they've been very clear here. The position of P is adjusted so the reading of the voltmeter is at its minimum value. Okay, so if that's the minimum value, then this is at a max, right? So the thingy is all the way over here. Okay, so it is 25 ohms that we're dealing with. Fine. So 25 ohms across there, and so therefore if it's 12 volts across the whole thing, then that means that V across here must be 12 take away 0.5, so that's 11.25 volts. Cool. So therefore the current's in the circuit, because everything's in series, so it's fine. So it's just going to be V divided by R, so that is 11.25 divided by 25, and that gives me 0.45 amps. Fine. So that's also the case for the bulb as well. So therefore R of the bulb is going to be equal to V over I, and so there's 0.75 divided by 0.45. Give me 1 point something. 1.67 ohms. 8.2, we have a graph of current against voltage. Now, even before I look at the question, I know it's probably going to try and catch us out by, we have a curve. People always get caught out with this. So the graph looks something like that. Get this into your heads now, boys and girls. We never draw a tangent or calculate gradient for these graphs. Never, ever, 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 ever. The gradient gives you an idea of what is happening to the resistance, but the value of the gradient doesn't give you anything. So we're just being asked for the resistance when the lamp is at 8 volts. So R is equal to V over I. This is all this question is doing. It's just testing that you know this fact here. So it's going to be 8 divided by, what's that, 1.7. Nice. And that gives us 4.7 ohms. 8.3, why the resistance of the filament lamp changes? Oh, nice and easy question. This is a year 9 question. This is, isn't it? So as current increases, rate of electrons colliding with metallic ions increases, causing them to vibrate more, further impeding, that was a good word, flow of electrons. And I guess we could also say in here temperature increases. 8.4, we got the same graph, right? What are we being told? P is moved to position Y. Okay. Oh, no, it's not. Sorry, it's different. Do you know what? I am going to draw it properly this time. Oh, this is taking entirely too long. I told you. Okay, what are we told? P is moved to position Y. Okay, so why didn't they just draw it like that then? Whatever. Okay, voltage across the lamp is 12 volts. Oh yeah, they're in parallel. Right. Okay, so this in essence is now just a parallel circuit. So I'm going to draw this over here. It's just going to there, isn't it? It's just a normal parallel circuit. That's all. The ammeter is just for the bulb at the top though. So if I was to redraw this, it just look like this. Sometimes it's a good idea to redraw circuits so things are a little bit clearer. Okay, calculate the total resistance of the circuit. Nice. So I'm going to guess that we want V total is equal to I total times R total, and then we're going to just find those out. We could also use our, 1 over R total equation. There's probably 2 ways of doing this. I don't know. Let's have a look. What are we told? We're told that this is 12 volts. Everything's 12 volts. Okay, so we have V total, and its resistance is 6 ohms. Okay, we are probably going to have to use our equation. Oh, and this is 25. Okay, fine. So let's use our 1 over whatever. So 1 over R total is equal to 1 over 6 plus 1 over 25. Can I be clever with that? Nah, really not worth it. And so therefore just doing the reciprocal at the end, I end up with R total is equal to 4.8 ohms. 8.5, calculate the power transferred by the battery. Okay, so we could use VI, but we don't have I, so we're not going to use that. We could use I squared R, but we don't have I, so we're not going to use that. So we're going to use the other alternative, V squared over R. So that's just going to be 12 squared divided by 4.8. Easy peasy. So that is just 144. So it's just 144 divided by 4.8. And we end up with bang on 30 watts. This is a very nice electricity question, actually. And then finally, we just have a wordy question to finish off. Oh no, it's the compare circuits. Oh my days, I hate these with a passion, which you probably know. Right, student wants to go to the dump. He gives 2 reasons why figure 14 is better. The parallel circuit is always better. That's always the way it goes, ladies and gents. It's always the parallel circuit is better than series every single time. But let's prove it. So parallel is better as PD across bulb can be varied from 0 to 12 volts. Series, do you remember the question said it can only go to a minimum of 0.75 volts? And again, that's going to be to 12 volts because when R is 0 for the variable resistor. That's it. We've said 14 is better, and we've given the reasons why. Happy days. Not too bad. So I hope you found that helpful. If you did, leave a like and a comment. And if you want to see paper 2, then click on the card and it'll take you there. And I'll see you next time.